to Lausanne, where he's now a professor. Clement will talk about the Ising model, discrete and continuous structures.
Good morning. Thank you very much for the introduction. I'm very honored by the invitation here and the chance to participate in this wonderful conference. I was wondering for 25 years what it would be like the first time I would go to Australia. And it's actually very nice. So what I'm going to talk about today is based on joint works with many people, most of whom are here, and a few others. So let me start by a question. It's a question that goes back to 8 years ago, to college actually. So when I was in college, I took a class in statistical physics and we saw the 2D, the Ising model. And that's the first time I heard about the Ising model, and I heard that the 2D Ising model had an exact solution. However, this exact solution was so complicated that it was out of the scope of the class to treat it. But still, I got very intrigued by that question. So at the end of college, I had to write a thesis, and so I went to professor, and I said, I want to work on the 2D Ising model. That's something I want to understand. And so he told me, well, it's a complicated story, you may be too young for that or something. So we worked on something else. But soon after, I told him I was going to do my PhD with Stas Smirnov. And he told me, oh, that's great, because actually he's working right now on the 2D Ising model. And you will understand something about it. And he told me, but there is something I really want to understand. So the professor was Belarus, and he told me, there is something I tried to understand about 20 years ago, and I couldn't. And you should definitely have a look at that question. The question was conformal field theory. And so he told me, there is a link between 2D Ising model and conformal field theory, and for mathematicians, it's black magic, because it's based on quantum field theory ideas, and it's highly non-rigorous, and that's something that I heard about 20 years ago, and I don't understand it. So this question, took about 8 years to answer, but I think it's more or less understood now. So I quickly understood that we have to add some things. The thing that is connected with conformal field theory is the scaling limit of the 2D Ising model at criticality. And to be even a bit more precise, scaling limit of wide fields and curves. So this question is the plan of the talk. In this talk, I'm going to explain a little bit, what this question means and what the answers to this question are. Okay? So we keep the question here, and let's start with the beginning. What is the Ising model? Okay, what is the Ising model? So the Ising model is a model that lives on a graph. Okay. So it's a model on the graph. More precisely, it's a random assignment of spins to the vertices of the graph. So it's very simple. You have a graph, finite graph, like that. And on the vertices of this graph, you have random spins that are either +1 or -1. Okay? The spins interact via the edges of the graph. How? Well, the probability of the spin configuration is given by a Boltzmann wave. The probability of the spin configuration is proportional to exponential of minus beta times some energy. where beta is a positive parameter, the inverse temperature, and H is minus the sum over all pairs of adjacent spins of the product of the spins. So what does it mean? Well, let's compute the energy here. Here you have two spins that are plus one. So the contribution to the energy is the product of the spin with the minus sign, so you get the minus one contribution to the energy. Here you have a one, here you have a minus one here, you have one here. So the total energy in this picture, say, is 0. Okay. So what are you doing? You're penalizing high energy configurations because of the exponential of minus beta H. And the energy measures the local disagreement between the spins. So effectively, what you're doing is you're favoring local alignment of the spins. Well, finally, the prefactor is just the partition function, which is just there so that probability is sum up to 1. Okay. So you're encouraging spins to be aligned with their neighbors, and how much you encourage them depends on beta. So that's what the Ising model is. The natural question when you do statistical mechanics is, what does the model look like when the graph gets big? You imagine that these little spins are like atoms with two possible orientations, and they try to align on their neighbors, and you ask whether there's a collective phenomenon. Okay, so now let's discuss 2D Ising model. So, you know, what happens when the graphs get large and approximate some physical shape. So that's what a 2D Ising model is. So what is it? You just take as a graph, in your definition, a discretization of a continuous domain. So you take a continuous domain, and you intersect it with a fine square grid of mesh size delta. Delta is the size of a little square. Okay? And that gives you a graph, and you look at the Ising model on this graph. So here is a Markov chain, whose stationary measure is the Ising model measure, approximately. So the Ising model is the still picture, okay? The Markov chain is there because it's nice, and also because it allows you to, it's the way to sample the Ising model that is efficient, okay? So that's how the 2D Ising model looks like. So here what we have is we have plus ones, plus spins drawn in white and minus spins drawn in red. And you have plus boundary conditions. The boundary spins are plus 1. Now, this little bar here is the temperature, is the inverse temperature, the beta. Okay. So, natural question to ask is, do we see anything interesting as the graph gets big? In our language, do we see anything interesting as the delta gets smaller, as the pixels get smaller and smaller? Do we see anything interesting? And the answer is that it depends on beta, what we see. So let's move a little bit beta to see what we get. So here beta is fairly small. If I move beta up, we'll see something interesting that happens. You see that the picture starts looking very different. Actually, you see that now spins tend to segregate. You have clusters of red and clusters of white. Actually, if you wait for long enough, the white will just take over. And because the boundary is fixed to be white. But you see a very different picture. Okay. So depending on the value of beta, you see something that's quite different. Actually, this was made precise and rigorous by Gonzaga in 1943. There's a very clear answer to the question what happens as delta goes to 0. So there is a phase transition that's a special value of beta, which in this case is equal to half of log of root 2 plus 1. Okay. So there is a phase transition such that the behavior for beta larger and smaller than this beta critical is drastically different. So basically for beta beta critical, the system is basically disordered. So what does it mean? Well, you have local effects, and the influence of this local effect stays local. What it means here is that a spin here will still influence its neighbors a little bit, but it will have zero influence on what happens at large distance. While if beta is large, what you see is a long-range order that arises. So the local effect propagates somehow and makes global spin alignment arise. So that is fascinating, but very well understood. Question that has remained more mysterious is what happens at the value, what happens at the critical value of it. So what happens here? So it will take some time to converge because the critical value is special, and this is not yet a picture of how the model looks like, but in a minute or two we'll see. That's the question. So what happens for this 2D Ising model if you take the Ising model at beta equals beta critical and you let the mesh size go to 0? So something that was noticed quite early by Onzaga, actually, is the emergence of power laws. That's a striking phenomenon. Most quantities that you will compute will decay as delta goes to 0, as the distance gets large, but they will decay polynomially fast. So the result is that what this idea suggests is that fluctuations will occur at all scales. As a result, you can expect to have scaling limits. You can expect that as you zoom out the picture, you get some random continuous objects describing the limit of the model. So it's a bit like a random walk. If you look at it from far away, you will see a point in motion. So here, for the critical Ising model, you expected to see some continuous random object describing its limit. So that's the object that is connected with conformal field theory in the question. Okay, so what random objects? A simple random walk, obviously, there is only one continuous random object that describes it well, it's the Brownian motion. Here it's less clear what would a limit of this guy be. What is it? What is the nature of the object? And so the answer is that there are several objects that we can look at. So perhaps the most natural are the fields. So what are the random fields of the model? You have these plus and minus ones. You can think of them as a plus minus one valued field. So this random field can hope that as the mesh size goes to 0, converges to a random generalized function, for instance. So that's one class of objects we can look at. Another class of objects, which have been studied more recently, is the curves. So what curves? Well, you could think level lines of fields, for instance, are curved. The most natural curves probably are interfaces. If you look at the boundary of a red island, it's a closed curve. And you can hope that this closed curve has a scaling limit. Continuous random curve. Okay, so these are the main objects we're interested in. So, that's the question. Can we study this limit? And here's a general statement, a general informal statement, which is that the fields and the curves of the critical 2D Ising model, there are actually lots of them. They have explicit conformally invariant scaling limits. Okay. So I have to explain what these terms mean, what I mean by explicit and what I mean by conformally invariant. So let's start with conformally invariant. What is it? symmetry in 2 dimensions. The reason is, in a nutshell, is the Riemann's mapping theorem. Let me just remind you what this is. So if you have 2 simply connected domains of the plane, proper subdomains of the plane, then if you fix 2 points in them, there's a unique conformal mapping that will send the first domain bijectively onto the second domain, and send the first point on the second point, and have a positive derivative. So conformal means bijective holomorphic. Visually, geometrically, it means it's preserving angles locally. It's allowed to do a lot of things, obviously, because you can deform any domain into any other domain, essentially by Riemann's mapping theorem. So that's what a conformal symmetry is. And being conformally symmetric is hence an extremely powerful property. Because if you understand, say, a model on just one domain, you understand it on all the other domains, at least for simply connected. So what we mean informally conformal invariance of these scaling limits means this. If you look at the scaling limit of Ising-model on the first domain, U, that's a collection of random objects, random curves, random fields. If you look at the scaling limit of the Ising-model on the second domain, that's another collection of objects. These collections of objects are related in the following sense, that if you map the object by the conformal map from the first domain to the second domain, you obtain the scaling limits of the Ising-model in the second domain. So the image of the scaling limit of Ising-model by the conformal map is still a scaling limit of Ising-model in the image. And so by equality, what do we mean? So these objects are not very symmetric a priori. And this doesn't look particularly symmetric. So what we mean is that the law underlying these objects are symmetric. So the probability measures are the symmetric object. So that's the informal statement. And now I want to go more precise and actually give results that go in this direction. So let's start with the simplest result, which was a question that was asked by Gonzaga. What can we see about correlations? And I'm going to try to make this question as narrow as possible at the beginning and then broaden the picture. So let's take a smooth, simply connected bounded domain. Okay. Let's take a point A in it. We're going to look at Ising-model with plus boundary condition. So we force the boundary spins to be plus. And again, that's for concrete. And now we're going to discretize a domain by a fine square grid, and we're going to identify A with the closest vertex of the discretization. And we are going to ask, okay, what can we say about the spin at A? Okay. So we want a number. So let's first ask the question, okay, what is the average value of the spin here? So in other words, the question is, how is the influence of this boundary on this spin? This spin, if you don't put boundary conditions, will be 0 on average. Half of the time plus 1, half of the time minus 1. Okay. But now you have these plus spins on the boundary, and really the question is, what is the influence of the boundary? So that was an open problem for a long time, but we solved it 2 years ago with Chalkak and Zurov. So the answer is that it goes to 0, polynomially fast, like 1 over the mesh size to the power 1 over 8. Like the mesh size to the power 1 over 8. And so if you renormalize the quantity by this mesh size to the power 1 over 8, you get something fairly explicit. So you get a constant times the geometric term. So the constant is lattice dependent. In the case of the square lattice, we can compute it. And the geometric term is is the hyperbolic length element, or the inverse conformal radius, if you prefer. So it's a quantity which is, as you would expect, conformally invariant. And also, for concreteness, here's what it is in the unit disk. So it's something that blows up as you get closer to the boundary. You expect that because as A gets closer to the boundary, it should become more positive because the boundary influence should increase, right? So this renormalized expectation indeed blows up as you approach to the boundary, like the distance to the boundary to the power of 1/8, invert, minus of 1/8. So here's just a good picture of Escher to help visualize. So what happens in the case of, say, the Ising model on a disk? So informally, if you want to compute the expectation of the spin here, you look at the fish there, and the size of the fish gives you an idea of the renormalized expectation of the spin. So I'm cheating a bit because this is not exactly conformal invariant. Escher thought it was, but it's not. But you know, it's a nice picture, and you know, the idea is right. Okay. So you know, maybe we can visualize this even a bit better. So here is a simulation of the Ising model on the square. And what we're doing is we're running this Markov chain, and we're averaging the spins we've seen so far. And we're then renormalizing everything to increase contrast. So I think this picture is nice because you start really with the Ising model. And in the end, you end up with something that obviously looks related to conformal geometry. Or at least you should, because but there was but the video will stop in a few seconds. The reason is there's a guy. I was running this simulation for a week and a half, and there's a guy who came to replace a cable, and he pulled the plug by mistake. And so that's where the simulation ends. But okay. So that's you know okay. So it's nice because you can see really this conformal invariance with your naked eye on the picture there. If you just wait long enough, that's the message. Yeah. Okay. So that was one result. Actually, you have more results for. If you ask, okay, how is it once the value of one spin related to the value of another spin, for instance? You know, how is this guy influencing that guy? You can again compute, show that you know this influence decays as the mesh size goes to 0, like the mesh size to the power 1/4. And if you renormalize by it, you get again fairly explicit formulas. So it works with different boundary conditions. So I put plus here to break the symmetry and make it easier to understand. But if you don't put any boundary conditions, you can also prove that you converge with something. And I wrote, for instance, a formula for this something for the 2-point function. So the 2-point function is given in terms of the 1-point functions and the hyperbolic distance, which is the only conformal invariant distance between the spins. Okay. So this quantity blows up like the distance to the power 1/4 when the x and y merge, and yeah, otherwise it's really explicit again. That was the conjecture of Cardi of 1984. So okay, so these are the kind of results we look at. So more generally, what we infer from these results is that the spin field, once you renormalize it by the mesh size to the power 1/8, converges to something, and more precisely, we understand this in the sense of correlations. It can be understood in, you know, more, you can add some topology that's not very hard. But so for all correlations, we get that the correlation, if you fix n spins, you ask how are these spins correlated, you can study how they are correlated in the limit, and you have a limit that's pretty explicit. And that works with various boundary conditions and it's fairly general. It works on multiply connected domains, etc. So I said that's one field. What kind of other fields could you look at? Well, the story started when we looked with Stas-Smirnov at the energy field, which is easier to study, actually. So you ask, okay, this Ising model has an energy. That's the energy. And so this energy is made by the edges, as you remember. So you can ask, okay, how is this energy distributed across the model? How much does an edge contribute to the energy? And the answer is that you can study this also. And the energy field, when properly rescaled, also has explicit limits. Something interesting here is that this field has limits in the sense of correlation, but doesn't have, you cannot put topology on this result. So there is no random generalized function that has this correlation. So that's quite interesting. Okay, so these are the kind of results we got about explicit limits for the field. So now I'm going to give a few ideas of the proof of this result. They are fairly long, but there are a few ideas worth spreading, I'd say. How do you prove, say, a result like that? So there are mainly two steps. The first step is to actually prove that the logarithmic derivatives of the left-hand side converge to the logarithmic derivatives of the right-hand side. After that, you'll have identified the logarithmic derivatives, so you'll have identified the derivatives, the logarithms up to additive constants. And so you will have identified the limits up to multiplicative constants, and then you need to fix the constants, and that's another step. I'm just going to give a sketch of the proof of this first part, just in the case of the one-point function with plus boundary condition. So how does it work? So we would like to prove that this guy, properly renormalized, converges to what it should be. So as I said, we look instead at logarithmic derivatives. So what are logarithmic derivatives? On the lattice level, derivative, it just means a difference. So you look at the difference between a spin. Sorry, the minus one should be outside of the ratio. So you look at the expected value of a spin and the expected value of the spin that's just one lattice step away. This ratio, again with a minus one outside of the fraction, converges to the derivative of the spin divided by the spin, so logarithmic derivative. So you want to show that this guy converges to that. Yeah. So how does it work? The key step is to reformulate this quantity in terms of an object that will scale well. You want to prove that something converges. Right? So you have to rephrase this thing in terms of something that scales well. And so the idea is to reformulate this quantity in terms of some special values of a discrete holomorphic function, a spinner, actually, some function with a square root-like behavior around the spin you're studying. So it's a function of an extra variable. And when you evaluate this function at a special location, you get the quantity you want, okay? So this discrete holomorphic function, you can actually forget about the easy model once you're there, almost. You can extract a lot of information about it and formulate it in an abstract manner as a solution to a discrete boundary value problem. Okay? So this is nice because discrete boundary value problems have natural continuous analogs. It's a lot of work to show that the solutions converge, but it can be done here. And so your discrete holomorphic function converges to the solution to a continuous boundary value problem. You find explicitly what is the solution to that continuous boundary value problem. And then you want to relate this to that. So this was the special value of that. So this should be a special value of that, except that you have a singularity, so actually you have to renormalize a bit. But the coefficient in the Taylor expansion of the explicit solution will basically give you this number. Okay, so that's more or less the strategy for the first parts of these proofs. For more points, it works similarly. So the key step, the step that I left completely mysterious at this point, is how you connect the lattice model with discrete complex analysis. So that's, I'm not going to go too much into the details, but just to give a few ideas of how this goes. So how does this connection star work? So how do you connect this to a spinner on lattice level? So the idea is actually a fairly old idea, is to use lattice fermions. This solution of Hongler, which I wanted to understand when I was in college, is actually very, very complicated. It was simplified a bit later by Kaufman, and she formulated it, it in terms of spinners and fermions. And for about 50 years, people rephrased, every generation rephrased this idea of Hongler, initial idea of Hongler, in a simpler and simpler language. And okay, so it's a bit hard to explain what this fermion is in formal terms, but you can think of it as a kind of deformation of the model. So here's a picture of a deformed Ising model where spins are not plus minus ones anymore, but instead they live on a square root type surface. And that's a kind of probabilistic realization somehow of the model view, of the things you're looking at here. So the idea is that what you want to do is you want to phrase this quantity in terms of some statistics of the loops of the Ising model. That's fairly simple. You just put a net between two spins that are different, and you get a collection of loops. You formulate your question in terms of these loops. Then you deform your set of loops, and you get a deformed collection of loops where you have loops, but also a simple path. And you deform the statistics of these loops, and you get complex valued things. And you prove that these complex valued things are actually discrete holomorphic at the critical value. Okay, so basically you get some lattice analog of Cauchy-Riemann equations using combinatorics on lattice, by making local rearrangements between pictures. You can prove that you have a lattice analog of Cauchy-Riemann equations. So, okay, in a nutshell, that's how these things work. So there's a miracle here. Obviously, a miracle that initially was discovered by Hongler, but took many, many years to be rephrased in a way that scales well. Okay, and that is actually fairly visual. Okay, so that's in a nutshell the idea that allows you to connect the model with discrete complex analysis. After that, the rest of the proof is also quite interesting. There are many special features here. Priori, your boundary value problem is kind of unstable. Boundary conditions are unstable. Everything is unstable, but thanks to a lot of miracles, you can actually control everything and get, I must say, miraculously, survive all the traps that are in front of you and prove that you actually converge to the right thing. Okay, so that's basically all I wanted to say about how we can study explicitly the scaling limit of the fields. Okay. So that was the first 5 years after this discussion I had with my professor. For me, conformal field theory at this point was just explicit. Okay, it means we can study explicitly the things. Okay, that's not what conformal field theory is about, only about, but that's the understanding at this point. So let's just discuss the other part, the curves, okay? This is also fairly visual. So what are the random curves in the model? Again, there are several types of random curves, actually many types of random curves that can arise, but perhaps the most natural and simplest ones are interfaces, in particular interfaces generated by boundary conditions. So what I mean is that if you take a domain and put plus spins on one arc of the boundary and minus spins on the other arc, you can then look at ID model on the discretization of this domain and trace an interface that has minus spins on its left and plus spins on its right. So it's describing the boundary of spin clusters. So it's a random curve because the Ising model is random. And you can ask, what is the limit of this curve? Okay? So you can do this in various setups. You can put free boundary conditions, and you can get some curves. And so here is a very informal theorem that these curves have explicit scaling limits. They converge to curves that were invented by other Trump to actually describe scaling limits of conformally invariant models. So it's a one-parameter family, and the curves here converge to SLE kappa with kappa equals 3. So, okay, so I'm not going to define SLE here. I'm just going to give an idea of how we can identify the limits of these curves. How we, they turn out to be SLE, but how does it work? How do we get the limits? So there are 2 steps. The first step is a pre-compactness step, where you want to make sure your curves are not too crazy as the mesh size goes to 0. You control them, so once you control them enough, you can say, oh, let's take a limit. Let's take a limit along some sequences. So we have a continuous random curve. It's not smooth, but it's Hölder regular. So take a limit like that, and now you want to identify it. Well, we want to show that we know what this curve is. So the idea is that we're going to parameterize the curve and then make it grow from one boundary point to the other boundary point. And more precisely, we are not going to look so much at the curve, but rather at its complementary. Okay. So now you look at the domain minus the curve up to time t, so it's a shrinking domain. And so now how do we identify this collection of shrinking domains? The key is the martingale technique. So you want to control how the curve grows. So what information you have about the curve? A priori not much, but the key will be to find some quantity that behaves kind of in a compatible way as the curve grows. So you want to find a martingale. So you want to find a quantity that is a function of the domain that's being slitted by the curve, and you want this quantity to behave as the curve grows as a martingale. What is a martingale? So a martingale is just, informally it's a fair game. In a physics context, the appropriate way to think about it is conserved quantity. It's not conserved deterministically, but it's conserved in law. Okay. So that's what a martingale is. So how does it work? Say this martingale for the limit will come from the lattice level. So basically you find a martingale on lattice level and you prove that it has a scaling limit. So what is an example? You take a spin here and you ask, okay, what is its average value knowing what the curve has done at this point? So that you can prove is a martingale on lattice level. And if you can prove that this average value of the spin has the limit, and that's exactly what we've done in the first part, in the fields part, you can actually get an explicit quantity that behaves as a martingale. Actually, you just don't get one, because it works for any x, so you get a one-parameter family martingale. And that turns out to be enough, if you have explicit values for what this guy is, to identify the curve. Okay? So in a nutshell, that's how these proofs of convergence work. You find some stochastic analog of a conserved quantity for the curve, and that allows you to identify the curve. Okay. So what about all the curves? So I spoke about curves generated by boundary conditions, but what about all the other curves? So it turns out we can also study them. Here's a theorem, which is not published yet, but it's in very good progress. So the collection of all the Ising model loops converges to a collection of random loops. It's called conformal loop ensembles. It was introduced by Sheffield and Werner. And if you have also arcs, you also have stochastic processes describing these arcs. And so the theorem informally is that all the collections of all the loops converge in the right way. So I'm not going to give details about this proof, but It's a bit more challenging than the previous one in some sense, because you cannot grow anything from the boundary a priori. The loops here don't even touch the boundary. So you have to use some tricks, and here the trick is to couple this collection of loops with another collection of loops that touch the boundary. And basically you can enter the domain using the auxiliary loops, and these loops touch the auxiliary loops, so you can enter the domain. And once you enter the domain, the excursions that these loops make can be identified using the first part. So that's how it works. Okay, so you know, that's the kind of things we did, you know, for some time. And so again, I told you, at this point, for us, conformal field theory was just a collection of exact predictions. Okay? We had no idea how the magic works there. Okay? So people made exact predictions, physicists made exact predictions, but how they did it, the reasoning they used, is not used at all. Okay? So I think it's a quite interesting question to actually understand how conformal field theory works as a theory, because it's actually more general. It doesn't work only for Ising model. You know, the reasoning is general, and it's quite spectacular. So you start just from a critical model scaling limit, and you end up with exact formulas, which are formulas with proofs. But how does it go? So informally, I'm going to try to summarize in one slide how a conformal field theory works. I don't know how understandable it will be, but I wish I had that one slide when I was studying the subject. So the idea is that you're going to try to describe your model not with curves, but just fields, and you're going to take as an assumption here that your fields form an algebra in some sense. And you know, what kind of fields you have? The spin field, the guy we studied, the energy field, which describes the energy, but the way the energy is spread across the domain. But you have infinitely many fields. I mean, simplest examples of other fields are just derivatives of these fields. They're also fields, right? There's more than just the derivatives, but okay, these are, just to give an idea, there's an infinite number of fields here. Okay, and one of those fields is particularly important. It's called the stress tensor. And so it's a special local field. It's just one of them, none of these two, that represents geometrically the action. That represents geometric actions. So what do I mean by that? I mean that if you take, it's a field such that its correlations actually have some geometric interpretation. So it's a bit hard to explain with a simple example what happens, but you can think, okay, you know, what if you want to deform the metric of some problem? What kind of problem do you want to look at? Maybe Dirichlet problem. You want to deform the metric, so it changes the Laplacian. If it changes the Laplacian, it also changes the Dirichlet energy. And the Dirichlet energy is the kind of energy you could use to do statistical mechanics. It's called the Gaussian free field, the object you would get. So the idea is that if you deform the model, if you deform the metric, you deform the energy in some sense. And deforming the energy, if it's localized, will amount to add some field at some point. So that's the informal idea behind it. So they take as an assumption that all these things exist, okay? But that's a reasonable assumption in some sense, at least for physicists. That's perfectly reasonable. And the miracle what happens in 2D, where the fact that you take as an assumption, again, conformal invariance, now it's again an assumption, so a statement, but it's an assumption. This assumption gets translated into this, the fact that this field becomes holomorphic. Holomorphic, not in the probabilistic sense, more holomorphic in the sense that its correlations are holomorphic functions. So if it's holomorphic, you can look at this power series. Okay. Okay. What you can do is that you can actually make this the modes, the lower modes, so the Fourier modes, if you want, of this field act on other fields by contour integration. Okay. And you construct an action. This way, you construct an action on the space of local fields, and the modes actually satisfy commutation relations. They form a representation of the Virasoro algebra. So the Virasoro algebra is an infinite dimensional algebra with this commutation relation, and so they identified, okay, that must, if you have a critical model, it must correspond to some Virasoro algebra. I think it corresponds to the parameter c equals 1/2 here. And then they say, okay, now we have this. What do we want to do? We take, again, as an extra assumption that you have a quantum field theory underlying it. And because you have a quantum field theory, a natural quantum field theory, you should have a scalar product such that the LNs, the modes are adjoints of the negative. And if you add this extra assumption, you actually get the classification of the representations satisfying this assumption. And so the classification of the representations actually gives you two things. It gives you a set of critical exponents and a collection of linear relations that give you PDEs for correlation functions. So using these two things, using PDEs that the formula should satisfy and critical exponents, you actually obtain exact formulas. Okay, so that's informally how it works, so it's fascinating. The question is, can you make sense of any of this? And the answer is mostly yes. For Ising model, at least, you can make sense of a lot of the parts of this reasoning. Okay, these are mostly ongoing projects, but the message is in some sense that yes, you can find the lattice analogs of these quantities and make the reasoning work. Okay. So finally, where does it lead us? Well, an exciting thing which is in progress, it's proving Zamolodchikov's conjecture that the Ising model is very complex. It has all this Virasoro structure. It has extra structure actually, and there's a conjecture. There's a hidden E8 structure behind the model. So E8 is the Lie algebra. The question arises when you try to break the spin flip symmetry. So you look at the Ising model with an extra external field. And this is conjectured to have a connection, very quantitative connection with the E8 algebra. And okay, that's the message. Simple models, they possess very complex structures, and actually, there's a lot to be discovered. So thank you.
Thanks very much for a very illustrative talk. There's time for questions.
Yeah.
There's a microphone.
You mentioned that every time you encountered a miracle and you could proceed.
Yeah.
So obviously integrability must be somewhere and must be responsible for some of your miracles. Where is it?
I would say it's not only integrability, but yeah, it's here. It's here. It's just right here. Discrete holomorphicity. The fact that you can recast something in terms of discrete holomorphic things is a sign of integrability. Let me explain to you in just 1 minute why. Once you manage to formulate things in terms of discrete boundary value problems, these discrete boundary value problems are linear problems with a number of variables that is just proportional to the number of sides, right? So it means that you manage to formulate quantities about your model in terms of solutions to linear problems whose number of variables scales just with the linearly with the size of the problem. So that's one very strong version of exact solvability, right? So where we use it is in the proof. Where we use the exact solvability in the Yang-Baxter sense. We don't really use it in the Yang-Baxter sense, more the star triangle sense, and it's really in the proof. And these lattice fermions are discrete holomorphic. That's really where we use the integrability. But we get relations for, the Ising model is integrable for any value of beta. We get linear relations no matter what the value of beta is. Now, when beta is beta critical, these linear relations are holomorphicity. Okay. Yeah. Thanks.
So all this works for the square lattice, right?
Yeah, so most of this can work for other lattices. work, say for hexagonal lattice, it will work. For very nice lattices, it will work. Some of the parts of the proofs will break down for non-symmetric lattices.
But you believe the results are so true.
Oh yeah, absolutely. The only thing that will be different are the constants. The curves will be exactly the same, and constants will be different. Yeah, thanks.
So this relates back to the first question. So integrability, there are many other models that are integrable for which you can't make the progress you've made that you can make for the easy model.
That's right. That's right.
So do you see any hope that could be?
There's definitely hope. So I can tell you what the problem is, okay? But there's definitely hope. That's unquestionable. There is hope. So the problem is that you have some relation. You can formulate analogs of these things for other models. The problem is that you have relations, but you have less relations. So as a result, you're not able to go from here to there. You're not able to forget about the model and say, we have characterized it uniquely as a solution of a collection of linear equations. We don't have enough equations. Okay. So there are many ways we could hope it works. So either find extra equations that the quantities don't satisfy, or use the fact that all these models are one-parameter families, and use extra parameters to get informations. Those would be natural hopes. Another possible kind of idea is to make rigorous sense of renormalization ideas, because abstractly these models should have limits, no matter how your constructions are needed to show that you have limits, but there's no reason why these models should not have limits. We have good qualitative understanding of their properties. They should have limits. We are not able at all to relate the fact that qualitative properties should imply limits. But that's another set of ideas which, if it works, would work in any dimension. Okay, so I'm not extremely optimistic about those ideas, but those would be other ideas. Yeah, well, that's what if you want to prove the lattice models have limits. Now, another point of view would be you're just not so interested in the lattice model. You want to understand field theories. The reason you look at lattice models is you want to have concrete instances of field theories. So if you try to do it this way, you could hope to look at find new lattice models that would have the right universal limits, and that already would help.